Okay, away we go. The recording's going. Welcome, everybody. Thanks for playing in the CTF. And if you didn't play in the CTF, you're probably going to find out now all the interesting things we got up to and why you should join in next year. And by the way, if you see interesting things presented here in the chat, you can still load up the CTF website, which is ctf.gnuradio.org. All of the challenges are still playable, except for the ones that were in person here in Knoxville. So 90% of the challenges are remotely playable and will remain online for the foreseeable future. And if you get through all of this year's challenges, well, there's also 2023 and 2022 available. So what I'd like to do for this walkthrough section is have lots of audience participation. So I want to see how players solve the challenges in this CTF. And so I want people to not be afraid to show off their super ugly, super janky solutions that just barely got you what you needed to get the flag. Doesn't matter at all. The only thing you need to get your points in a CTF is the flag itself. So if you wrote something that was good enough to get the flag out, that's good enough for today. So let's start with people in the room. Who here in the room has something they'd like to show off? Vlad? Vlad, you had your hand up earlier, so come on up and we'll get your screen shared. All right, should have the presenter permissions now.
Okay, oh boy, let's hope this works. Okay, yeah. All right. Is that working? Okay. Yeah, so I guess I'll show you guys how to hack the mics next year. They've actually been the same, I guess, since GRCon24 at least, because I originally did this in GRCon24, and this year when I saw that challenge pop up again, I was like, I wonder if this has really changed, and I don't think it has. Because, well, if I still had that computer, I probably could have used the same flow graph I used then even, but I didn't have it, so I had to rebuild it. But it's really straightforward anyhow. There's actually not much to these mics, as you might be surprised to find out. You're looking at right now my little instrument for actually receiving them. So right now I just have like a raw file instead of my hack RF, which I was using to receive it. But basically, they really are just analog. They're analog FM. It's weird. It's not quite narrow, not quite wide. It must be like 25 or 30 kilohertz deviation or something like that. It's kind of odd. And the only thing that makes them special is that they have this funny subcarrier on them, this like 30 kilohertz BPSK subcarrier that is sending some kind of short sequence on there. Clayton and I were theorizing it might be literally DCS, but just shifted up to a higher frequency. So it's, supersonic. So it gets filtered out. You don't hear it. But otherwise, there's nothing really special about it. And the worst part is it would appear that there's not any sort of rolling key or anything like that on there. I literally think it's just some kind of it could be a 5-bit identifier for which mic is on, because all you have to do is basically play that signal back and then you're in. So this flow graph here that I'm showing you right now is my receiver for sort of preparing that data. So what it normally does is there's just like a resampler frequency shifter to get around my DC spike in the hack RF, and a low pass filter, and then an FM demodulator And actually from there, I have two filters, one for the audible part of the signal so I can listen to the mic. And then the other one actually filters off that little BPSK carrier and saves that to a file so that I can play it back later. So if I run this, there we go. Oh, I think it must be off frequency a little bit. I must have messed with something. Hold on. Maybe we'll try moving that. Well, that's the actual carrier right there for the signal. I must be slightly off. Yeah, I've shifted my, oh, hold on. Oh, yeah, there it is. So that one sounds really crappy because this recording I made before I realized I needed to move around the DC spike in my SDR. So it sounds really crappy because of that. But this is the receiver. So in the bottom, what you can see is the blue trace is the unfiltered audio signal. And then the red trace is actually the signal that I'm high passing and saving off to a file. So basically what I did is I just loitered and recorded that for like a minute or something. And then I went to my transmitter. So the transmitter is also pretty simple. It's basically, you know, the logical inverse of that. Of course, I had a couple inputs here. I had both a wave file source and a microphone source that I could mix together, just, you know, to have a little bit of fun. But the important part here is I have this file source that is also added. So that's that subcarrier that I'm injecting back into the signal. So I recorded that file earlier, and then I just sum it with my audio, and then I just frequency modulate that entire thing and send that out. And just as long as you have that funny little carrier slapped on there, it works just fine and gets into the mic system. The only issue is that the mics are actually rather strong, and it kind of surprises me. So next year, I'm going to bring some amplifiers. No, but I think you have to bring your SDR like right up to the receiver antenna, or it really doesn't break in very well. So, yep, that's all I've got. Any questions?
What was the flag like?
What was the flag like?
No. Where did you find the flag?
Oh, well, he just gives it to you.
Yeah, in this challenge, the challenge description just said, you know, get your audio into the microphones and I will give you the flag. So I just you know, had a piece of paper, showed it to him, and he put it into the scoreboard. We did that for a couple of the challenges, like the one where you had to hack the walkie-talkies, same thing. As soon as you proved that you could do it, then I would give you the flag. Okay, well, thanks, Vlad. Another question?
Yeah, I am wondering, like, if you didn't already suspect that there was something like the subcarrier that it ended up being, like, what if you could describe like a methodology for determining that was even there?
Yes.
Repeat the question.
So yes, the question is how did I figure out that there's a subcarrier on there that has some important information? That is a good question. So if I'll actually go and play that recording in here. Bear with me a second. GQRX and its interface. Okay, here we go. So again, ignore the fact that I accidentally recorded this over the DC spike. But if you go ahead and zoom in here. Okay, so this is what the mic audio looks like on the air. So this is just my recording of it, right? So, you know, obviously the first thing I did is I grabbed my SDR and I just started sweeping the spectrum, looking for stuff that might look like audio, right? So I looked at a lot of FM signals. They're pretty recognizable, right? So once I got up to around 500 megahertz, I saw a few conspicuous signals that look like they could be it. And what especially helps is when you start zooming in on them, you'll see, like, as the presenter is talking, you'll see the modulation move, right? So it's like, okay, it's probably one of these. There were a couple mics on, so you had a couple options to pick from. So then when you zoom up on this and you look at this, well, you notice something interesting. Normally an FM signal only has one carrier, right? It's just the primary, it'll spread out as it's modulated. But if you look at this one, it's kind of conspicuously got three, right? There's these two funny side lobes. And so you might think that those are like additional frequencies or something. But if you know a little bit about FM, you might realize, oh, that actually might be a subcarrier, right? If there's basically the frequency that response that's produced by an FM signal is actually governed by something called a Bessel function, but won't get into that. But basically, the modulating content of the FM can cause these subcarriers to appear, or carriers on the sides, rather, these side lobes. So what you do to get at those, and this is generally a good idea when doing this sort of stuff, is you can just put a wideband FM demodulator on it. So in my case, did my screen share drop off?
Yeah, it looks like it.
Sorry. If you go back to the receiver, you see I just have a quadrature demod on here. And then I have start without a low pass filter. And basically you'll be able to see from DC to daylight, if you will. So if you just demodulate the FM, you'll be able to see if there's any other stuff riding on top of it. So in my case, I just did that, and I saw that up at 30 kilohertz, there was a carrier. And the way you might also suspect this is if you look at like broadcast FM, there's like a 19 kilohertz pilot tone, and then the AM, there's an AM signal up at 38, and then there's RDS up at 50 or something?
57.
57. Yeah. So it's not uncommon for FM signals to have all sorts of carriers on them. Sorry, very long-winded answer, but hopefully that answers your question. Okay.
Any other questions? And I'll check let's check the chat, see if anyone had a question there. Any questions in chat? Don't see any, so thank you very much, Vlad.
All right.
And that's actually this conversation about subcarriers in FM signals makes me think, I wonder if anyone wants to present solutions for the on the broadcast bands challenge, because that was a lot more of the same.
I did have one question. I was just thinking, do we know the model of the mic? Like, do we look up what chipset it's internally or something?
The question was, do we know what model the mics were? Did anyone take a picture of them or know what they are? I don't know.
Somebody posted it in the CTF chat, actually.
Okay, yeah, Vlad says somebody might have posted it in the CTF chat. I suppose you can go by and ask Barry. I think he's still tearing down the AV stuff, so he might be able to tell you what model it is. Okay, so before we carry on and open it up to anything, does anyone here or in the online chat have a solution to the broadcast bands challenge that they would like to show off? Because I think that would tie in very nicely to the conversation we're having right now. Broadcast band, anybody? Anybody on remote? Okay, we'll come back to that if we need to. All right, let's open it up to any challenge, anybody. So we'll start with the remote people. Anybody remote would like to present something? I'm just realized I have a few remote users that are still locked, so I'm going to unlock you so that you can access the chat and everything. Yeah, I think everybody's unlocked. So anyone on remote want to present something? Anybody local want to present something? Come on, you know you want to. All right. What else? Oh, how about Daniel? You created at least one of the challenge tracks. Is there anything that you would like to show off to get the ice broken here? We'll see what Daniel has to say.
I'm incoming. Yeah, I have a huge feedback on the audio. Anyhow, yeah, I can present about the Not-Lora challenge.
Okay, Danny, I'm just going to bring my microphone over so that the room can hear you, and I will give you presenter permission. Make presenter. Okay, you should have access now.
Okay, let's see. I think that's screen 1. Yes. Is it working?
Yep, we can see your screen.
Okay, great. So let me start by showing you the Sigma file. Probably that's the best way to begin. And the idea of this challenge was to have some analog voice signals that were spread using the same kind of Chirp spread modulation that LoRa uses. And that's the reason the challenge was called Not-Lora, to suggest the idea of LoRa. So these are not LoRa signals, but they resemble LoRa in a way. So if you look at the spectrum, you can already see some of these chirps. And if you go to the trouble of measuring them, perhaps with the cursors here, you might notice that the chirp duration, which is 4 point something milliseconds, if I do it very accurately, matches one of the standard LoRa configurations, and the bandwidth as well is 125 kilohertz. So the idea of using LoRa is to try to make the challenge easier. If you know about LoRa or if you search online, then you have this table of spreading factors, and there is a formula to calculate the chirp duration and the chirp drift in hertz per second, which are the parameters that you need to de-chirp the signal, because this in here is not a LoRa signal, it's an FM audio signal, but it's chirping, so moving up the spectrum in the same way that a LoRa signal would do. How can you notice that this is actually an FM signal? If you look closely at some parts of the recording with the appropriate parameters here, I'm not sure if I'll manage. Yes, so I don't know if it comes well enough on the screen, but here this is a little bit wavy. Here maybe it's easier to see. So this is the frequency modulation, the FM audio. When I'm talking on the audio and giving the flag, it's also moving the frequency of the signal. So in this way, you are able to notice that there is something going on. And also in here in the middle, this is the most obvious flag. This is a narrowband FM signal, no chirps, no nothing, which says none of the signals in the challenge are LoRa, and it gives you the very first flag in the challenge, which is easy. And it's also intended as a way to get you thinking about FM, and this is plain FM, so maybe some of the other signals are FM. And in fact, in here you can see some of the patterns of the FM audio. The way to solve this challenge is to de-chirp the signal. So to de-chirp the signal, you need to know the chirp rate. And to do things properly, you also need to be aligned in phase with the chirp, because basically you want to generate the same chirp but without FM modulation, and multiply against the complex conjugate of it to remove the chirp modulation. If you are off in phase, that means that if the chirp that is on the signal is going like this, but I'm here on the chirp I'm generating, you will get frequency jumps. For some of the signal types, it doesn't matter that you get frequency jumps. Basically, you have like another copy of your signal, some 100 kilohertz away, let's say. But for FM, it does really matter because it's frequency modulation. So if you are very off in phase, you get some voice, but it's very difficult to understand. So you need to fine tune the phase, and I think the best way to do that is on radio. You put some QTQ slider or entry, and you do this interactively and try to adjust the parameter to get clear audio. So this is the first flag, and then depending on the way you go, there's here another signal. It's quite apparent that it's chirping differently. And again, you go back to these LoRa configuration tables. This is spread factor 9, which is one of the most popular, and this is spread factor 11, which is the maximum and the one that people use for long range communications. And you can also see here, there's something definitely going on with the signal. This one is amplitude modulated. So there's a nice trick here. You don't even need to de-chirp the signal. I didn't notice when I was preparing this, but since the whole thing is amplitude modulated, you can just GQRX or whatever receiver and do amplitude demodulation, and it sounds fine. And that's also a clue for another challenge unrelated to this one. So that gives you two of the flags. And you also have in here the other one, two of them are missing, which are the most difficult ones. Where could they be? If you have been looking attentively to the signaling here, then you might see that there is a second one, which is much weaker. This is not an artifact. In fact, for example, this other signal doesn't have any other signal. This is a second LoRa signal or LoRa-like signal with the same chirp parameters. It's just at a different phase, so that means that they are well separated. You can see it here. They occupy different parts of the time frequency domain. So if you use the same chirp parameters as for the first one, but for this second one, you need to change the phase, and then you will get a weaker FM signal that you still can manage to hear and get a flag. Something I did when putting together the challenge is to put all of these signals at different frequencies, and the frequencies are like random numbers with many decimals, so nothing sits at an exact frequency. And for fun, I also threw in some symbol rate offsets. So if you do with the standard LoRa parameters, the things will slowly drift. And for most of the flags, that's not really a problem. For this weaker one, it starts to be noticeable, and it the way in which you notice is it keeps shifting in frequency. So if, for example, you are looking at this with GQRX or something similar, you need to chase the signal on the spectrum because it moves, I don't know, a few kilohertz per 20 seconds or whatever. And the final flag is in here in this seemingly empty area of the spectrum, which might be a clue that if there is an empty area here, there might be something hiding. And it's actually fairly difficult to notice. I don't know if I'm seeing some of the chirps or if I'm imagining them on the spectrum. This is spread factor 7, so it's a faster chirp rate. That makes the chirps more vertical, so they are more difficult to see. It's a weak signal as well, like this one, and it's modulated in SSB, so single sideband. That means that when I'm not speaking, there is no signal, and the amplitude of the signal is proportional to my voice modulation. So only when I speak strongly, there is a strong, the signal is stronger, and it might pop up above the noise floor. But regardless of whether you've noticed that there might be some signal here or not, you might want to try doing some common LoRa spreading factors. So this is spreading factor 7, is another of the common ones. And if you chirp with that, you will see there is something. Then you adjust the phase, single sideband. And single sideband, as in the case of AM, is also quite tolerant to frequency jumps, so you don't even need to adjust the phase of the chirp so accurately. It will just work. Something also to show, I don't have like a proper solution to my own challenge, but maybe I can show the way in which this is generated. I did everything on a ground radio flow graph, which is kind of unusual for me when preparing these challenges. I often do everything in Python or most of it in Python. This is everything on a ground radio flow graph. So you can see here the WAV files with the flags in audio, and a couple of them are narrowband FM. And the trick here are these vector sources, which have these variables. Basically, they are the chirp patterns for the different LoRa spreading factors. And when you multiply your signal by one of these, you are chirp spreading it. And these polyphase ARPs are to apply these sampling frequency offset that I was mentioning. So some of them, as you can see, have some resampling, which is different from one. And the way that I was interactively checking if this challenge was feasible, for example, if the weak signals were strong enough and clear enough that they would still be possible to be understood, is that in the end, I was basically taking one of my vector sources, applying the same kind of delay that I have here on signal generation, the same kind of resampling, and then multiplying the whole signal by my chirp. So the chirp in this single signal, then I got some version of the chirped file, and this I listened to with GQRX to check that everything was nice. And basically the solution of the challenge, I think, was to iteratively produce these the chirpings and then listen to the signals as you wished. Any questions?
Vlad has a question in the room. Go ahead, Vlad.
So I didn't hear your whole explanation very well, so forgive me if you already answered the question, but what, in my case, and I think Clayton's and several others, when demodulating some of these or de-chirping them, you would get a really bad buzz on the signal that actually made it rather hard to understand, though I think you could pick the flag out of it. What was the cause, and how do you properly avoid that?
Yeah, so in case live stream didn't hear that, Vlad is asking that when he and I built demodulators for this, we had a lot of trouble with a lot of buzz making it through. Usually, 1,000 hertz buzz if it was in the case of the spread factor 9. And wondered if you had any way that you were able to get around that or minimize the amount of that buzz that made it through.
And it's specific to the FM. It doesn't.
And yeah, we noticed it seemed to be worse on FM compared to the other AM or single sideband.
Yeah, I sort of mentioned that briefly, but I can go into more detail. So the reason is the following one. Let's say that you are the chirping this weak signal, and the chirp you generate locally to the chirp is the strong one. So that means that for most part of the chirp period, the frequency difference between these two is going to be this positive value, let's say, depending on whether you add or subtract. But for this part of the period, you end up with a signal on one specific frequency. But then what happens is one of the two chirps, since they are slightly out of phase, gets to the top before the other one. So in here, you are doing a different subtraction, and things wind up at a different frequency until this one jumps again, and then you have the previous configuration. So the signal you obtain when de-chirping is basically for one portion of the time is going to be at a steady frequency, let's say here. And for the other portion of the time, it's going to be at a different steady frequency, let's say over there. If the phase difference between these two is very small, that means that most of the time the signal is at a single frequency, but then it quickly jumps to a different frequency and jumps back. why this is so problematic on FM in comparison to AM or SSB, because FM is about frequency modulation. So if there is any frequency jump, then FM is going to notice and the other ones are not. Also because FM, when you don't have any signal, you just have noise because your signal has jumped well away in frequency. The thing you listen in FM is very strong noise. The thing you listen in AM, if your AGC is not fast enough, is quiet noise. So that's mainly the reason. And the problem goes away in as far as you adjust your phase of your the chirp and chirp. So basically what happens, and the way to do this interactively in a good way, is the two copies of the chirp signal that you get at different frequencies. Their powers are proportional to how much percentage of the time the two chirps are, let's say, aligned, and how much percentage are disaligned. So if you play with the phase of the chirp and chirp, at some point the second signal will become weaker and weaker, and the audio quality on the main signal that you're trying to listen to will improve.
All right, thanks, Daniel. Any other questions? And I'll just jump out here and see whether anyone has a question in the chat.
It seems not. It seems that the chat is clear.
Yep. Okay, well, thank you very much, Daniel. While we're on that topic, I could show, I have a receive flow graph that I used while I was beta testing the challenge for Daniel. And let me see.
After you show that, I actually do have a follow-up question, because I'm sure Daniel will know something too.
Okay. All right, where's my screen sharing? Wait, why do I not? I don't know why I don't have a screen share option. Oh, take presenter. I guess I got to take it back from Daniel. Okay. Share screen. All right, hopefully my screen share is coming through. I'll turn this back on. So here's an example flow graph that I used to demodulate. In this case, we're demodulating the FM chirped signal. And so I'm bringing in the Not-Lora signal up here at the top, just converting it to complex. And down here at the bottom is where I have my chirp generator. I'm just starting with a sawtooth waveform. And then these few blocks here are just basically implementing the formula for a chirp. And then I put that through a phase modulator and multiply. So this is multiplying by the inverse chirp. The one interesting thing that Daniel mentioned is that you would normally need to be aligned in phase when you're de-chirping. So you'd need to have your negative chirp in the same alignment as the chirp of the incoming signal. But I found an interesting way around that, and that's so I have this resampling block here. The incoming sample rate was 525 kilohertz, but I knew that the bandwidth of the chirps was 125 kilohertz. So this resampler converts the signal down to 125 kilohertz. And that way, if you hit the edge of the band, you just circle around and end up on the other side of the band. And once you do that, you don't need to be aligned in phase anymore. And after you de-chirp, if you're off in phase, then the result is that the frequency will be off of the signal that you recover. And so I just saved my signal out to a IQ file and then opened that up in GQRX. And I can show what that would look like once you open up the signal in GQRX. Oh wait, I gotta check what the file name is. So let's say for the single sideband, here's my solution 5.cf32. And it was at 125 kilosamples. And it switched to an upper sideband. And you can see there I must have been a little bit off in phase with the chirp that I was generating, because this signal is a little bit below the center line in terms of frequency. So I think that's what happened there. I did have, in my flow graph, I do have a parameter where I can adjust the initial phase of the signal source here. And you can see that I've been kind of filling in random phase numbers and just trying to get it so that this output signal was centered. But I just thought it was interesting to show that by resampling it down to 125 kilohertz, matching the bandwidth of the chirp, you could get away with not having to be aligned in phase. All right, and Vlad, you said you had another question for Danny?
Yeah, I was wondering if there was any strategy for automatically synchronizing.
Okay, yeah. So Vlad asked whether Daniel had any strategy for automatically synchronizing the de-chirp signal to match the chirp.
Yeah, I think you can try to do it in the same way that a LoRa receiver does synchronization, which is basically the same that Clayton was showing. The key is if you are resampled to 125 kilohertz, then you can measure your phase difference by the frequency error you get when de-chirping, assuming you are correctly tuned to the signal to begin with, which you can do by eye or by detecting power if you want to do it programmatically or whatever. So I think that's the key, and it's actually how a LoRa receiver uses the packet preamble for phase synchronization, symbol phase synchronization.
Yeah, so I guess it's automating what I was doing by eye, right? I'd see it's a bit low, okay, I'll decrease the phase. A bit too high, I'll increase it. Yeah, there's also a formula probably. So if you measure the signal, it's 2 kilohertz off, you can plug that in a formula and it will say twiddle the phase by this many radians. Very nice. Okay, any other questions for Danny in the room or on the live chat? I see in the live chat that FlameWires also, I think, resampled it down to the chirp bandwidth. Very good. Okay, so thanks again, Danny, for showing that off. Let's see, who do we have next? Anybody on the live stream who would like to present something? Oh, and I see Michael has joined. Let me just unlock you so that you have the ability to chat. Anyone on live stream want to present? Somebody raised a hand. Jonathan, let me give you presenter permission, if I can find you in the list. Oh, there you are. So, make presenter. Oh, okay. Jonathan doesn't have anything to share. That's fine. All right. No, looks like nobody in the remote. Anybody in the room? Anybody at all want to show off something that they solved? Okay. Nobody in the room either. So I guess I can talk a little bit about some of the challenges that I put together and maybe show you kind of intended solutions, that kind of thing. First off, for anyone, I guess the remotes will not have seen the foxes before. So I'll just hold those up to the camera. So the foxes were these little beacon transmitters that I put together. There's a flag printed on the lid, and inside the case here is a Adafruit feather board that has a radio board built on. And there's a little lithium battery. Maybe I can expand my... Yeah, you're welcome to look at the other one. Okay, hopefully we're seeing that better on the screen. So, yeah, up at the top here is the Adafruit board. It's got this little radio board built on, which is capable of doing. It's designed for doing FSK and ASK and some simple modulation, but it's also got a mode where you can just on-off key the thing. And so to do that, you need to hook up one extra wire. So I have a little wire connected from a GPIO pin over to the on-off keying pin of that radio. And then I just wrote a little bit of Arduino code that runs on here and taps out a flag in Morse code. And you can also see it blinks the light here, so I can kind of get some visual feedback that it's running. So you can almost read the flag off from the blinking light there. And then just a little lithium battery powering the thing. And for anyone who didn't see it, there was the flag printed on the top of the thing. And there's, of course, lots of different ways that you can go about locating one of these hidden transmitters. I usually get by with nothing more than an RTL SDR and an SDR application like maybe GQRX, and just kind of walk around playing the game of warmer and colder, look for when the signal gets stronger, and go from there. It can be really useful in GQRX to disable the automatic gain control so that the amount of audio that you get is proportional to the incoming signal strength. And that way, when you get closer, it'll sound louder in your headphones. And if you get farther, it sounds quieter. And I also find it really useful to pay attention to the input gain. Normally, as soon as you hear the signal, you want to turn your gain down as low as you can when you still hear the signal, and then get as close as you can to the signal before it overwhelms your front end of your receiver, and then turn the gain down again and keep working your way closer to your target until you eventually find it. Sometimes you find that you get, you're within a few meters of your target, and now, no matter where you are, it's overwhelming the front end of your receiver, and then you can just unscrew the antenna, and that gives you an extra, 50 or 60 dB worth of attenuation. And then you might need to crank the gain back up, but then you can keep zeroing in on your target. So that's kind of how I approach finding these hidden transmitters. We were talking earlier about demodulating FM subcarriers. So maybe I'll show a little bit about the FM subcarrier challenge that I put together. Let me just set down the microphone so I can use my hands here. All right. I'll have to share my screen again. Take the presenter mode back. And open the screen share. Yeah, hopefully the remote can see the screen. Somebody scream in the audio chat if you're not seeing it. So let's go to... All right, here's my weird FM signal, and let's bring up So what was it? Broadcast FM. We'll have a peek at I'll make this a little bit bigger. Let's start by just having a peek at the SIGMF meta file just to see if there's anything interesting here. We see that our sample rate is 480,000 samples per second. Nothing else interesting up here. And the frequency is 98.7 megahertz. So you can see that this is probably going to be an ordinary, the challenge was called on the broadcast bands, and you can see it's on a frequency of 98.7 megahertz, which is exactly in the middle of the FM broadcast band. So if you had to guess, you'd probably assume this is going to be something like a broadcast FM signal. So my favorite tool to use for receiving these kinds of things is GQRX. And to open up the file here, you just go into the mode of opening a complex sampled IQ file, and I'll put in the file name of the SIGMF data file. So throw that in. Oops, I didn't copy it right. Copy. I don't know why it's not pasting. SIGMF data, we knew the sample rate was 480 kilosamples per second. And our center frequency was 98.7, not that it matters too terribly much. And we expected it's probably a broadcast FM, so I'll just go to, let's say, mono FM, wideband. So here we go with the audio. Now let's see. You probably can't hear it very well, but if you look down here in the decoded audio spectrum, you can see this little spike popping up. And it turns out that's actually Morse code playing. Maybe if I put a little bit of a waterfall here in the audio, you can see that little spike there with some Morse code. If I load the file back up from the beginning, we'll probably be able to hear it at a lower frequency at the start. It's maybe 8 or 9 seconds in. And we get a little bit of Morse code. I can hear it. It's kind of high frequency, so you might not hear it if you're out in the audience there or on the live stream, but you can very clearly see this little Morse code signal there. And if you listen to it, what you're going to hear, or what you're going to decode, is kind of like, hey, this is the start of the challenge, and the flag is, but you're not going to get the end of it, because eventually this thing keeps increasing in frequency until it gets up to about 15 kilohertz. And 15 kilohertz is the limit of what the audio that's in a broadcast FM. It only preserves audio from 0 up to 15 kilohertz, and anything beyond that, you're not going to be able to hear. So if we want to get around that, actually, what? I think I need to plug in my laptop before I run out of battery. Good to see you. All right. So we see that CW signal that was kept increasing and increasing in frequency, and eventually went beyond 15 kilohertz so that we couldn't see it, or it looks like it's going beyond 15 kilohertz. So we're probably going to need to demodulate the FM signal and look at kind of what's at the baseband. And if you've ever looked at all at how things like FM stereo and RDS work, the way they work is that they encode information above the 15 kilohertz of audio that you normally that your receiver normally decodes. So for stereo signals, there's a pilot that's at 19 kilohertz. And the stereo information, like Vlad mentioned earlier, that's up at 38 kilohertz. And then up at 57 kilohertz, there's some RDS data, that binary information that displays things like the call sign of the station, the name of the song that's currently playing, all that. So in order to see all of those subcarriers that are higher than the 15 kilohertz, what we need to do is do an FM demodulation of the signal, which will transform it to the baseband version of the signal, and then we can visualize that and have a look at it. So I have a flow graph here. I'll just open up all the flow graphs here, including my solution flow graph. And so here's what we're doing. We're going to take in the SIGMF data file. We'll do a quadrature demodulation. So this is an FM, it basically demodulates the FM and returns the baseband signal to us. So this is for one of the later parts. I think I have, so really all we need to do is these two steps, and we can send the baseband audio out to a file and look at it. This is for a later part of the challenge that we'll get to. So let's take a look at what happens after you apply this quadrature demodulation step. I think I have a baseband version of the signal in here. Yeah, so here's our demodulated audio. So let's open that up in Spectrum. And the sample rate here, I think, is 240,000 samples a second because I downsampled by a factor of 2. And I'll just adjust my limits here so we can see a little bit better what's going on with the signal here. Zoom out. And I'll increase my FFT size a little bit so we can get a little better look at things. And now what we see, there, get a bit nicer color on the signal. So what you can see once you demodulate this, we're looking at frequency on the vertical axis. So down here at the bottom is 0 hertz, 10 kilohertz, 20, 30, 40, 50, and so on. And on the horizontal axis is time. So you can see here we're looking at about a 10-second time span. And the audio that you hear when you demodulate that FM signal is down here at the bottom. So the first 15 kilohertz you can see is that music that was playing, which didn't seem to have any flags in it or anything. And you can see it's nicely filtered, so it cuts off right at 15 kilohertz. But you can also see here this Morse code signal happening here, and you can almost read it off by eye. Maybe if I increase my if I increase the FFT size one more and scroll across, you probably start reading that off by eye. So you can see here's like PART1. So this is part 1. The flag is, and eventually we get into the flag itself, ELECTROMAGNETISM. So the flag is electromagnetism. And you can see the reason why we could kind of only hear it while it was down here in the audio, but then it disappeared, is because it extends way up here to, a little over 30 kilohertz all the way at the end. The reason why I put that Morse code diagonally like that is because I wanted to kind of gently lead you beyond the 15 kilohertz and suggest that, maybe there's something out here in the beyond for you to find. And if you do that, sure enough, you can see that there's at least, so it looks like 3 other signals in here. So after you get your first flag, you can see that there's 3 more things left to be found. That flag up at the top, maybe if I go one more step bigger on the FFT size and scroll down to where it is, maybe we'll be able to read off some of the, there we go. it's upside down, but we can read off the letters anyway. So if we go back here, flag C5, EA1, 8, 3, and so on. So this was just a flag that was painted in to the spectrum, and I snuck that in up here around, looks like 57 kilohertz, right where RDS should be. So yeah, normally if you were looking at an actual broadcast FM signal, normally there'd be a data carrier up here. It would be phase modulated, and it would look a lot narrower than that. But yeah, just for fun, I put in this flag there. And part of the reason why I put that in particular at 57 kilohertz was kind of to suggest to you that this is not flame wires. You have something to tell us? Okay, when we get to FSK, the spikes as well as the separation on 2FSK are an indication that the modulation index of 2FSK are a whole number. Ah, yes. I didn't even notice that myself until you pointed out how interesting it looks. Okay, so let's jump back into it. And where were we? I think I had, that's a different in spectrum. So I'll jump back over to the signal here. So we already saw flag number 2, which was up there at 57 kilohertz where RDS is normally supposed to be. And let me zoom back out. And you can see somewhere here around 40, looks like centered on about 44 kilohertz. We have this signal here, and I'm sure somebody in the room can tell me what modulation that looks like.
It looks so much like
sideband. Lower side, yes, lower sideband. So you can see it almost looks like, if you looked at a spectrogram of a recording of your own voice in something like Audacity, it looks very much like that, except you can see there's more energy up here at the top versus the bottom, which tells you it's probably in the lower sideband. So as you go higher in frequency with your voice, it gets lower in frequency when it's modulated. So yeah, it's probably lower sideband. And so to test this out, when I was making the challenge, I used GQRX to decode that. So I'll just put in spectrum in the background, and we can open up GQRX. And I think I have demodulated complex data in this file here. So I'll open that up. And sample rate in this case was 240,000 samples per second. So GQRX wants to deal with complex data, which is why I'm loading in a complex file now instead of a real valued file. So we're going to see all the signals copied. They'll be present both above 0 and below 0 in frequency. I'll just set my center frequency to 0 so we can see what's going on with that. And start things up here. So we'll zoom in on the positive frequencies because that's the part that we're interested in. And you can see, sure enough, up here at, let me go into sideband modulation or something. So you can see up here at the 57 kilohertz mark, that's where that painted flag was, and it's reading off. One thing, if you're trying to receive these things in GQRX, sometimes fiddling around with the FFT frame rate can be helpful. Right now, things look a little bit wide, and we're not going to be able to see too many letters of the flag. But if I was to drop it down to, say, 10 frames a second, now we're going to be able to, the letters are a lot smaller now, and so we'll be able to see a lot more. And of course, you can zoom in on the frequency axis if you want a wider resolution that way. So anyway, that was flag 2. I'll speed things back up here, and let's go listen to this lower sideband. Right now we're on the upper sideband. If ever you tune in with the wrong sideband to a signal, you're going to hear what sounds kind of like Daffy Duck. It sounds like there's, something intelligible and human there, but it just sounds weird. If you ever hear that kind of a sound, you just need to switch over to the other sideband. So Go to our receiver, and now we'll select lower sideband instead of upper, and we'll drag my frequency up here a little bit.
Part 3. The flag is Quebec, Echo, Uniform, Lima, Mike, Yankee, Whiskey, X-Ray, Delta, Echo.
So there you go. We get the flag out from that part. And then the last part is up here at 50 kilohertz. And Don was just talking about this. He was interested in the fact that it almost looks like two separate signals. It turns out it's just one. You can maybe see it a little better if we go into in spectrum, and let me zoom out on the FFT axis and zoom in on time. And you see how that looks. You can kind of see two discrete frequencies, and you can see us jumping back and forth between those two frequencies. In fact, you can almost you can start reading the bits off by hand almost. Maybe if we zoomed in a little bit farther. For anyone who hasn't seen how to do this before, you can actually do some demodulation directly inside of InSpectrum. And to do that, I'm just going to increase my FFT size a little bit so I can select the signal I'm interested in. Whoops. One more FFT size increase. So here's our FSK signal jumping back and forth between two discrete frequencies. If you right click and hit add derived plot, you can add a demodulator. So let's say we know that it's jumping between two frequencies, so we want to do a frequency demodulation to see that information. So we'll do a frequency plot, and then this is just adjusting where my center frequency is and how wide my filter is. So I can narrow down the filter by dragging on these edges, and I can drag my center frequency down. So we'll put the center frequency right in the middle of this thing, in between the upper and lower frequencies of interest, and narrow down our filter bandwidth. And now if we scroll down, you can see the demodulated signal down here at the bottom. And now you get a nice line graph there, basically. We can zoom in time. And now you can see kind of the individual bits. And here it's starting to get easier to read. You can see this is probably like 1 0 1 0 1 1 1 0 0 1 1 0 1 1, and you can almost read things off. InSpectrum even makes things a little bit nicer, because you can for one thing, you can now add a derived plot from this one, and you can add a threshold plot. And what the threshold plot does is if the signal is above 0, then it counts it as a 1, and if it's below 0, it counts it as a 0. So now instead of this kind of noisy, wavy signal, now we have a nice square signal there. And in fact, if I adjust my center frequency, I should be able to get things just lined up so that the 1s and the 0s are the same distance away from that center, and then the widths of these pulses should be about equal. The next super fancy thing that you can do in Spectrum is if you want to start decoding those bits, first we need to kind of decide where each bit starts and the next, where each bit ends and the next bit starts. And to do that, we can turn on the cursors. You may have seen Daniel doing this to measure the length of the chirps in the LoRa challenge, but you can also use it to measure the length of bits whenever you're dealing with digital modulation schemes. And so here I'm kind of measuring the width of, let's say, this looks like it's 1 bit worth of information. And if I get around close, you can see that estimating that this is 1200 baud, which sounds like a kind of a common baud rate and a convincing baud rate for what it might be, 1200 symbols per second. So that's just one symbol we're measuring, but if I increase this, we could do, let's say, 10 symbols. And now you kind of have this nice slider where you can make sure that things are still lining up. And yeah, 1200 baud looks like it's still lining up with our symbols there. Let's go to 100 bits, and you can see, look at that, I'm staying kind of perfectly aligned with my signal. And here's the really cool thing. Once you have this grid aligned, let's say I wanted to, decide, okay, that's a 0, that's a 1, 1, 0, 0, 1, 0. You can have Inspectrum do that for you if you just right-click on that, and then you can say extract symbols, and we'll just extract to the standard output, and you can see it read off all the 1s and 0s for us. So that's pretty handy. Once you have that, you could dump it into your tool of choice. Python is kind of my go-to, but a lot of people have been using CyberChef. It's a kind of a web application where you can dump information in various formats and manipulate it. I won't go through the whole thing here because it would take me a bit longer to select all the bits, but I'll give you an idea. Maybe we can at least get a few letters of ASCII out of this, and you can get the idea of how you would get the rest of the flag. Internet's a bit slow here, so it'll take time to load. Oh, it's mining Bitcoin. That's why it's slow. Okay, so we have some bits there. And let's see, we want to be able to deal with, we want to convert it from binary. Oh, maybe I want to remove the, we need to remove, who's an expert with CyberChef here and knows what I want to do to get from binary. Let's see, that's converting to a bunch of random characters. Sometimes if you delete, no, not a valid byte array. You know what, I bet I might need to remove the commas from that.
Oh, there's an option to select your delimiter.
Oh, was that in the binary?
Yeah.
Oh, okay. From binary, delimiter, comma.
And then there's like another one that was like remove white space or something.
Oh, okay. Yeah, let's try that.
You might be able to put that before that block.
Oops. Remove white space. That looks promising. Okay. Yep. Spaces, carriage returns, tabs. Okay. Yep. That's rid of that. Let's see if now we can go from binary, delimiter, comma. Oh, there. Okay. Now we're down to some bytes. Now the one trouble you run into when if you're trying to decode binary into something like ASCII, you run into the trouble of, where does each byte start? Each byte is 8 bits long, but we don't know which is the first bit, and we might be a bit off. So you can just start deleting bits and hope that eventually we might, there we are. So you can see at this point, what I have here has decoded to ASCII text of runt molit. The reason why you're seeing that is that I just used some lorem ipsum text here. So there's a few paragraphs worth of lorem ipsum followed by a copy of the flag, and then it goes back to lorem ipsum. So you're kind of forced to decode all of the bits before you can get your way to the flag. I do have an example here of a flow graph as well that can solve this. Let's see. Shut down my GQRX. So yeah, here's an example of how I was able to demodulate that in using a GNU radio flow graph. So what we're doing is we're reading in our broadcast signal, FM demodulating it, and then we want to pick out the signal that's 50 kilohertz above. And so I'll use a frequency translating FIR filter. We want to do a low pass, and our center frequency is set to 50 kilohertz there. And our bandwidth, I think it's set to about 2.4 kilohertz worth of bandwidth. Then we do another FM demodulation on that because we want to distinguish the low and high frequency tones that made up the FSK signal. And then I'm sending it into a symbol synchronization block, this is basically the automated version of the manual selection I was showing, where you line up to the start of each bit. And then there's the binary slicer, which is exactly the same as that slicing operation that I did in Spectrum, and then dump the bits out into a binary file, and then you can take that file and throw it into CyberShaft or Python or whatever. We have a question?
Yeah, I was wondering if you could go into the fields for the symbol sync block there.
Sure. Yeah. Yeah. So the question was, what are all the parameters here in the symbol sync block that I've used? The most important parameter to get right when you're doing symbol sync is this samples per symbol, because this is telling the symbol sync block essentially what the baud rate is of the signal that's coming in. If that's wrong, then nothing's going to work. So you have to kind of keep track of what your sample rate is up until this point, and then know what your baud rate is. So here I have a variable for my baud rate is 1200 baud. Set that here, so we know it's 1200 baud. And then we have to keep track of what our sample rate is. Our initial sample rate was 480 kilosamples. We do a frequency demodulation, so we're still at the same sample rate at this point, 480. And then when I do this frequency translating FIR filter, I'm filtering down to a very narrow band, so I can go to a lower sample rate. So I have a decimation factor of 50 in here. I actually used a variable for that, so you can see I've got my decimation set to 50. So at this point, our sample rate is going to be 480,000 divided by 50, whatever that is, 9,600 probably. Yeah, and that should be 9,600 samples per second at this point. And then we do another quadrature Gmod. That doesn't affect the sample rate, so we're still at 9,600. So now down here, we're at 9,600 samples per second and 1,200 bits per second. And so there's going to be, and if you divide those by each other, you find out that it's 8 samples per symbol. And I think I just have the formula here. We're taking the sample rate divided by the decimation and then divide that by the baud rate, and we get 8. So that's the important parameter. It tells it how fast the symbols are coming in. These others, I just left them all at the defaults, and I'm not an expert on this. These loop bandwidth and damping factors, those are control. There's like a control loop that tries to figure out whether it's sampling too early or too late and make corrections to get itself exactly locked on. And these kind of control how fast it locks on versus how inclined it is to stay locked on despite the presence of noise. Default values usually work, especially if it's a high, if the signal is at a high signal to noise ratio like it is here. So the parameters aren't really critical. The other thing that can matter is, like, depending on what kind of a signal you're receiving, whether it's like PSK versus QAM versus FSK, there are different modulator or different timing error detectors that may work better or worse. The timing error detector it's like a mathematical function that tries to estimate whether you're sampling too early or too late. And some of them work better depending on what type of modulation you're doing. I'm not an expert on this, so my usual approach is like keep trying them until I find one that works. You know, if you knew a little bit more about demodulation, you'd probably know which one you're supposed to use. If you were doing some kind of a PSK or QAM, you would need to have the correct constellation here for this timing error detection to work right. But we're dealing with something very simple, so just the default settings more or less work. So I would say if you're doing this, make sure that your samples per symbol is exact. Leave the other things at the defaults, and then twiddle around with different timing error detectors until you find one that works well for your signal.
Thanks.
Any other questions? I'll check the remote too to see if anyone has any remote section or questions. No, last we had was Don's comment. Any other questions in the room? No, okay. So that was FSK. Yeah, so we're about an hour and a half in, so it might not be a bad time to stop. But first I will check, does anyone else have anything they would like to show or a challenge that they really want to see the answer to, or how it was put together, or anything like that. Any requests? Oh. I'll wait for the chat as well. Anybody in the room? Okay, I'm not seeing anything. So let's carry on the chat in the chat room. If anybody has any questions about any of the challenges, bring them there. And we'll carry on the chat from there. I'll get this video posted up to YouTube. I would love to see write-ups written up in blog posts. I know some of you really like to do blog posts about things that you've solved, so I'd love to see those online. Oh, one more question from Jason Zed asking about how to demodulate SIG ID number 6. Jump into that for 1 second. Signal identification 6 was, actually I'll very quickly mention SIG ID 5 because the two are very closely related. Signal identification 5, if you solve that first, let me zoom out. You can see this kind of looks like some sort of a frequency modulated signal. If we zoom in and attempt to frequency demodulate it, you might see that it just looks like kind of a nice little squiggle down here at the bottom. Nothing too interesting. It turns out that it's actually using a 4-level frequency shift keying. So instead of jumping back and forth between 0 and 1, it's going between like 0, 1, 2, and 3. And it turns out what this is a digital voice protocol called M17. If you were in person, you might have seen me wearing an M17 button. That was kind of meant to be a hint that there might be some M17 challenges. It is a open source mode for digital voice that's gaining some traction in the amateur radio community. And it's kind of meant to be a replacement for things like P25, DMR, and other proprietary digital voice protocols that are used typically with walkie-talkies. So for this one, there's various M17 receivers that you can use. I think SDR Angel has a built-in M17 demodulator. You can also demodulate it in GQRX and run it out to a command line tool and demodulate the audio that way, which is what I did when I was testing out the challenge. But if you open up SIG ID 6, what you'll see is that it was a very similar looking signal. You can see again, looks like kind of a frequency modulated signal. You have the very same preamble and post-amble that you would have in SIG ID 5. So it looks like it's probably M17 again. But if you tried to demodulate it in SDR Angel, I don't think it has support for this. So it turns out that while M17 is normally used for voice, there is also a packet mode in M17. And the M17 specification goes into the details of how you would encode packet data in M17. And so what you just need one of the M17 demodulators that does have packet support. And the one, let's see, M17 demodulators, the C++ demodulator does not support packet mode as far as I know, but I used the one here in packet, or in M17. Oh, was it in M17 tools? No, I don't think it was M17 tools. It was M17 implementations. Yeah, so in M17 implementations, SP5WWP is Wojtek. He's the original creator of the M17 protocol, and he put together a C implementation. And this one has an audio encoder, an audio decoder, and also an M17 packet program. So all you have to do to decode the packet from this one is build this M17 packet program. It's just a little C program, and you can route the audio out. I just routed the audio from GQRX into this, or you can record it out to a WAV file and then load the WAV file into the packet decoder. But yeah, either way, as soon as you do that, it just prints out. It's like an SMS message that contains the flag, and then there was a bonus flag which just asked you which call sign was the destination call sign, I think. Yeah, so that was SIG ID 6. Any other requests before we finish? Let me go back to our recording. Anybody in the room? Okay, so let's leave it at that. I will stop the recording. We'll get this up onto YouTube and we can carry on. Oh, wait, one more question. Data corruption 7. Yes, I can show you that very quickly. So if we go to, where was it? Logo challenge. So here was the copy file. Let's just do a little quick hex dump of that file. So if you did the data corruption one, was, wait, which one was, yeah, I think number 7 was probably this one down here at the end. So you can see here at the end, there were several flags. There was this one that was just ASCII text. This one was hex encoded. And then if you look at these bytes starting right immediately after that hex encoded flag, these ones, all that's happened here is that all the bits have been inverted. So you can just XOR each byte with hex FF, and that'll invert all of the bits, and then you get your flag out. Pretty sure. Let's see. Like, okay, there's our bytes, and then if we do like XOR with FF, and then convert that back to bytes. Yeah, 7:FL, and yeah, if you carried on, you'd get the rest of the flag. So that was flag number 7. You just had to kind of carry on beyond the thing that you already found, and then the very next thing was also a flag. All right, any last requests before we finish off? Not seeing any in the room, so I am stopping the recording, and we'll see everybody back in the chat room. Bye.